Thanks to the organizers for giving me the opportunity to give these lectures. So I decided I would talk about inertial gravity waves interacting with background flows. So it's not quite turbulence, it's not quite wave turbulence, because the waves are going to be linear. But when the waves, linear waves interacting with background flows, you get interesting behaviors, including some phenomenon that look like a cascade or stuff like that. So there will be a connection to wave turbulence, and hopefully it could serve as an introduction to what Giorgio is going to talk about, giving lectures about pure wave turbulence. So the main questions would be how to predict the statistics of waves over a background mean flow. And I will be using inertial gravity waves to emphasize these results, but you could ask the generic question. We'll be focusing on a steady background mean flow. It's a linear problem, I've said that, so it's simpler than wave turbulence to some extent, but then you can make interesting connections. And I'll also like to make a connection to ocean dynamics, so pretending it's useful maybe to understand natural flows, but very quickly I will turn to highly idealized models on which we can get some explicit results. Okay, so there will be two parts, more or less the two lectures, although part one is going to be a bit longer than part two. So I will be studying first the near-inertial wave limit, that will define what that is, of inertial gravity waves and how they interact with background mean flows. And in the second part, I will be considering internal gravity waves, so another limit of inertial gravity waves over a weak background flow. Okay, and this work is, some of it is our recent work, but a lot of it, including what I will be discussing today, is strongly inspired by the work of Young, Benjelloul, Buehler, Van Est, Kafiabat, Thomas, and many others. Okay, so I'll start with a very basic material, because we have various backgrounds here, and try just to understand what I mean by waves and what I mean by mean flows. So maybe one starting point could be if you consider the rotating Euler equation. Okay, so if you're a physics student, write the equations maybe with arrows on top of the vectors. Grad P, where P is density, pressure over the constant density of the fluid. And I'm going to add rotation to this. So maybe F over 2 Ez times U equals minus grad P. F is the Coriolis parameter, it's twice the rotation rate. That's standard notation in geophysical fluid dynamics. I assume that rotation is along the vertical axis Z. Okay, and so you say, well, if rotation is fast, then probably this term is going to be really big. Should write bigger? Yeah? Can you read? It's too small? Too big, maybe? I don't know. Okay, you let me know if it's too small, too big.
Omega over 2, or you mean F? It's not F over 2. Yes.
F is 2 omega. Oh, it's F. Thank you. Thank you. Yes. Okay, so F is 2 omega. The rotation rate along the vertical. Okay, so you're going to assume this term is really large. You should balance it with something if you want things to remain divergence-free. Things are incompressible here. Okay, so you're going to write something like that. This is a geostrophic balance, right? And then you take the curl of that equation. Okay, and if you take the curl of that equation, we'll obtain that dz of u equals 0. So this geostrophic flow is invariant along the vertical direction, right? That's known as the Taylor-Proudman theorem to physicists. Although I'm really not sure how much of a theorem that is, and that will be my only use of the word theorem throughout these lectures. But basically, this flow would be invariant along the vertical direction. Okay? So that's the slow geostrophic flow, but you could ask, what if the initial condition is just not like that, right? what if the initial condition depends on z? Okay, so what if this function is z? Okay, and basically the answer is, well, you should keep the time-dependent term because you're going to have waves in the system. Okay, and if it's independent of z and very weak, maybe you want to linearize the equations. And you're going to get inertial waves. And of course, in the general setting, the waves are going to interact with the mean flow, and they're going to be two-way coupling, and you'd like to understand the statistics of the system. Okay? That's a very simple example. I'll move on just from this to an idealized model of the upper ocean. Where we will get the same combination of a slow mean flow and waves on top of it. Okay, so it looks something like this. It's a two-layer system. Make that big, maybe. There's an interface between two layers. Okay, the upper layer has density ρ1. The lower layer has density ρ2. There's a height of the interface here, which is h of x, y, and t. What else? It's rotating. Around the vertical, there's gravity. Okay, and I will describe this system using shallow water approximation. Okay, so the layers are shallow as compared to the typical horizontal scale of the flow, and so the horizontal components of the velocity field will be u of xyt, v of xyt, and they're much greater than the vertical component of the velocity field. Okay. So in this system, there is an equivalent to geostrophic flows or balanced flows. So here, geostrophic flows, they correspond to, let's see, equal horizontal flow in both layers. No, equal, exactly equal. That's what a balanced flow would be. There will be no deformation of the interface. What else? And there will be a tiny deformation of this upper free surface, which I will neglect. Okay? A tiny deformation of the upper free surface. This will be neglected. That's known as the rigid lid approximation. And this is negligible in the regime where the density difference is small as compared to the overall density. So this will be neglected because ρ2, which is greater than ρ1, right? It's stably stratified. And so ρ2 minus ρ1 over ρ1 is much less than 1. Okay? So because the densities are close, it costs little potential energy to deform that interface, but it costs a lot of potential energy to deform the upper free surface. Okay, so it's going to happen, but it's going to be a very weak modification of H that we're going to neglect. Okay, so same question here. What if the initial condition is just not like that? Okay, so what if the initial condition is flow in the upper layer only? then it's an unbalanced initial condition, right? It's not a geostrophic flow. And so we can study the subsequent evolution of the system, writing the shallow water equations for the upper layer only, right? So let's see. Yeah, so that's unbalanced. And so again, we expect some kind of wave dynamics in the system. Right, so we're going to consider a weak initial condition. So we're going to linearize the shallow water equation in the upper layer. Okay, and I'm going to use this notation UV for the horizontal flow in the upper layer. Okay. Weak means I'm allowed to linearize the equations. Okay. yeah. So then the rotating shallow water equation will be dt of u. Then there's the Coriolis force minus Fv equals, and here there's a lateral pressure gradient, okay, minus dx of p. And you can show using hydrostatic balance that this will be minus g prime dx of h, okay, where g prime is rho 2 minus rho 1 over rho 1 times g. So it's much less than g. It's called the reduced gravity. Again, you have the lateral gradient of the height of the interface. Okay, so as an exercise, you can show that using hydrostatic balance to determine the pressure. Okay, and similarly, dt of v plus fu equals minus g prime dy of h. Okay. So let's consider a simple case maybe where this initial condition is independent of x and y. Okay, so we have in mind that this would be the ocean. Okay, so you have the upper ocean, the mixed layer maybe of the ocean, but has constant density and is well mixed. And then there's an atmospheric storm passing by. Okay, storms have very large extent, maybe thousands of kilometers. Okay, it's passing on top of the ocean. The wind is going to drive the upper layer of the ocean, depositing momentum. So suddenly you have non-zero velocity, uniform as a function of x and y at the scale of the ocean because this storm is so big. And we want to study the subsequent evolution of that impulsive driving of the ocean by the storm. Okay? Well, so yeah. So if the initial condition is independent of x and y, then dtu minus fv equals 0, dtv plus fu equals 0. It's convenient to introduce this curly u, which is u plus iv, okay, complex velocity. And this equation plus I times this equation leads to dt of this u plus I f u equals 0. Okay, and the solution will be u equals some integration constant e to the minus I of t. Okay, so it's an oscillation at a frequency f, which is called the inertial frequency. Okay, so hence the name inertial oscillation. And so what does the motion look like? Well, it's easy to convince yourself that we're going to assume that m is real, right? It's a complex number up to a change of the time origin. I can pick it real. in which case u will be m cosine ft, v will be minus f sine ft, and now I can compute the Lagrangian displacements of the particle. That would be x dot, and that would be y dot for the motion of particles in a horizontal plane at the surface of the ocean. Okay, and so x of t will be some initial x0 plus m over f sine ft, y of t is y0 plus m over f cos ft. Right, that looks right. So the trajectory will be centered around x0, y0. You can see it's a circle. Let's see. So at t equals 0, if m and f are positive, I'm here. And as time increases, I'm going to go in this direction. Okay, so in the northern hemisphere, where f is positive, and I've also assumed m positive, it will be a circular trajectory and the motion will be clockwise. Okay, so those are inertial oscillations, and I will show you what that looks like in the data maybe, or I'll just, maybe I'll start with the data. Could you say that louder? Yes. I don't think I gave initial data on the position. There's no. Oh. You don't want this, why not? Oh, sorry, say again. Yes, okay, now I see it. Thank you.
Just call it, instead of x naught, call it xc for the center of the circle. That's what it does.
So this one is xc. Okay, I think and then you want, okay. Good point. That's what I'm going to do. Okay. Thank you. Okay. Now, can we see that in the upper ocean? Well, yes. So here you're looking at the trajectories of drifters, which are these buoys that are just drifting in the ocean, and they are tracked by GPS, so we know their position as a function of time. And you can see here the trajectories of the buoys following a storm. So there was a storm, and then they tracked the position of the buoys for something like 2 weeks. More than that, but they're showing the positions for 2 weeks. And what you can see is that there is this nice circular motion which corresponds to these inertial oscillations. It's in the northern hemisphere, so you should think of these trajectories as circling clockwise. And you can also see that there is a drift, okay? And this drift will be due to the existence also of a background mean flow, a geostraphically balanced flow that also exists in the system, in the framework of this model. Okay? Why do people care about these oscillations, which are called near-inertial waves? Well, because they contain a significant fraction of the kinetic energy of the ocean. What you're looking at here is mooring data, okay? So a line of sensors in the ocean. You're looking at the kinetic energy spectrum as a function of frequency at various depths. And you can see this peak here around the inertial frequency, which contains typically as much kinetic energy as the balanced geostrophic flow. Okay, so they have similar velocities, and so we expect the quasi-geostrophic flow to distort the wave field. Okay? And that's an important process because once you've distorted the wave field, then you have an inhomogeneous wave field in X and Y. And this.
What were you plotting before? Can you explain? So kinetic energy of what quantity as a function of frequency? So
It's the velocity spectrum
of what?
of a sensor on a line. There's a line of velocity sensors. You're measuring the velocity at a given point as a function of time. Okay, you're computing the spectrum. This is what any physicist would do, right? You have velocity, you compute the spectrum. With the spectrum, you look at the PDF, then you start thinking. Okay, that's what they did, which is what. Okay. So now it's measurement as a function of depth, and then it's a time depth diagram. I don't know if it's clearly visible here, but the claim is that once you have structure in the inertial wave field, it will be able to propagate downwards in the ocean. Okay, and so typically people would like to understand where the near-inertial wave energy will be accumulating as it's distorted by the background mean flow, because this is typically where, in the long run, you expect that energy to propagate to deeper region, induce breaking and mixing, and contribute to the stratification of the ocean. Okay, so I won't be discussing this process. I will just be discussing the horizontal organization of the near-inertial wave field in the system. Okay, so I should say maybe how we go from these purely inertial oscillations to near-inertial waves. Okay, so there's an additional equation you'd have here, which I should have written, which is the equivalent of mass conservation, which is the evolution equation for the height h of the upper interface. And if you linearize it, you get dt of h plus the divergence of hu, which will be h0, which is this depth of the layer at rest, times the perpendicular divergence of u equals 0. Okay? Yeah?
Basic question, but if you measure this at the surface of the ocean, how do you disentangle the fact, I mean, is it the surface gravity wave or is it the inertial wave?
The waves I'm talking about? Those are waves, it is not surface gravity waves. Surface gravity waves correspond to a tiny displacement here of the interface, and they would be extremely fast here. Okay, root gk. So those are interfacial waves here. Okay, that have non-zero velocity in the upper layer and deformation of the interface.
The spectrum you showed was for a point on the surface, right? For the vertical displacement?
It was for various sensors in a continuously stratified ocean. Just to show you, the actual ocean has a continuous stratification. And it was various depth, but pretty much at various depth, I would see this peak, shallow enough sensors, but yeah. Because that's the full thing, I was lazy. I considered an initial condition that was independent of x and y. Of course, if the initial condition has some horizontal structure, it's easy to look for eigenmodes, solutions proportional to e to the I k dot x minus omega t. Okay, that's a wave vector here. That's only horizontal directions. And you can substitute, compute the determinant. You want it to vanish. You get the dispersion relation that omega squared is f squared plus g prime h0 times k squared. Okay? So that's the full dispersion relation of these interfacial waves in the shallow water approximation. And so if the length scale is such that k squared g prime h0 over f squared is much less than 1, then this term is very small as compared to this one. Okay, f squared is approximately equal, omega squared is approximately f squared plus some small correction. And that's what we call near-inertial waves. It's not quite a pure inertial oscillation. Okay. And that happens when the typical scale, the typical wavelength is much greater than the characteristic scale lambda, which is a Rossby deformation radius. You can see this is a length scale squared. So root g prime h0 over f, okay, which is called the Rossby deformation radius. And for this shallow mixed layer, it's typically small, I don't know, kilometers to maybe 10 kilometers. Okay, and so any wave with a wavelength much greater than this lambda will be in the near-inertial wave regime, where its frequency is almost f squared plus a small correction due to dispersion. Okay? So let's see, a few questions. Okay, so how are we going to describe the interaction between a background mean flow, if now I want to include a fixed, steady geostrophic flow and see how the waves are distorted? How am I going to describe this in the absence of scale separation? Right? If there's an initial condition to begin with, then probably the background flow will imprint its scale onto the wave field. Okay, but then it means that this is a wave mean flow interaction in which the two components have the same spatial scale. This is not typically the situation we're used to. The comfortable situation is when the wavelength is much less than the typical scale of the medium, in which case you're in the WKB ray tracing approach, and we have all this machinery to study this problem. But here, I think in a breakthrough paper, Young and Benjelloul said, well, instead of a timescale separation, instead of a spatial scale separation, we can leverage the timescale separation to get a simple reduced governing equation for the wave field. Okay, that's what I'm going to show you next. Then once you have this equation, or generically you could ask, where is the near-inertial wave energy going to localize in this system? Okay, we said it's probably important for the subsequent propagation at depth. And so a large number of people gave arguments suggesting that probably the energy end up in anticyclones, and there's also data showing this. And one paper I like a lot is this paper by Danu van Es-Buehler from 2015. And actually this simple model here is directly from their paper. And they said, they gave arguments, which I will show you, that it should be in anticyclones. Although when we look at the data, it's not always in anticyclone, not entirely clear. So I'll try to maybe come up with something more precise than this. And so generically, we'd like to be able to compute the long time statistics of the wave field, some long time statistics. Maybe the wave kinetic energy, time average, the potential energy of the wave, time average, the Stokes drift associated with the waves. Okay, and so we're going to see how to do that in various limits in this system. Okay, to do this, the first thing I need to do is to derive this Young-Benjelloul model. Right, so I'm going to do that now. And I'm going to explain to you how this model comes about using a formal multi-scale expansion. Okay, so all this still holds. I'm just trying to make room here. So we will be considering the system in which there's also a background flow. And this background flow is balanced. So I say balanced flows have equal magnitude in both layers. Okay, so it's a background. Yeah, that's a background barotropic flow. I don't want to say that. Z-independent flow. I'll try to avoid jargon, but when you run into the oceanographic literature, it's kind of, yeah. So background Z-invariant flow is geostrophically balanced, so it's divergence-free in a horizontal plane. Okay, so it will be two components, U of xy stems from a stream function minus psi y, v of xy is plus psi x. Okay, its vorticity is the Laplacian of psi. So I should say, and if I write this flow with a capital U, the typical convention in geophysical fluid dynamics is to have a minus sign here, okay, which can be confusing at first. So I think it's not sure if it's the same convention than Anlor, for instance, but you know. Then vorticity is plus the Laplacian of psi for this background flow. Yeah, and this is maintained through geostrophic balance with a lateral pressure gradient. And so we're going to study, again, we're going to assume weak waves on top of this background flow. And so we're going to linearize the shallow water equations around this background flow solution. Okay, and the background flow is going to be independent of time as well. Okay? So let me do that. Yeah?
So you say first that the waves are excited by the unbalanced flow. So now you more or less change your setup. What excites the wave?
Yeah. No. I said the waves are going to be excited by a storm. So the waves are just the initial condition at t equals 0. So this is, previously I considered an initial condition which was a uniform velocity along x everywhere, okay, and no background mean flow. And we studied the evolution of that, and we just got a pure inertial oscillation everywhere. Now I'm considering uniform initial condition along u at t equals 0, but in a background state where there is already a background mean flow steady. Okay, so I will get these waves, but they're going to be affected by this background flow. Okay, so the evolution of the wave field will lead to different states that will have some structure in the horizontal, which I didn't have previously. Okay.
The structure in the horizontal can be any, or are there some particular assumptions in large scale variation?
The structure, we're going to be considering a flow eventually that is at a scale which is much greater than this lambda that I've defined. Okay, and by doing this, the flow will typically structure the wave field with wave numbers that are small so that the frequency is close to f, and I will be inducing near-inertial waves. Okay? Okay, so if I linearize the shallow water equations around the background mean flow, I will get, we had dtu minus fv. Advection by the background flow will be j of psi u, where j is the Jacobian. I know maybe here. J of fg is fx gy minus fy gx. That's a convenient way to write advection by the background flow. And then there will be u dxu plus v dyu. On the right-hand side is minus g prime dx of h, dtv plus fu plus j of psi v, advection by the background flow, plus advection of the background flow by the wave v perturbation equals minus g prime dy of h. And then the equation for h, dt of h plus j of psi h, it's advection of the perturbation by the background flow, plus h0 divergence of u. The background flow is divergence free, is 0. Am I missing a term here? No. That looks right. Okay. Then I'm going to non-dimensionalize the equations. Okay, use some. So we're going to non-dimensionalize. Yeah, say again? J is here. Yeah. dx of f, dy of g minus dy of f, dx of g. Okay? So that's the advection term, capital U dot grad small u, capital U dot grad small v, once you substitute the expression of u and v in terms of the stream function. Okay? So we're going to non-dimensionalize using the length scale will be lambda, okay, which was written still, I don't know, root g prime h0 over f in the horizontal for x and y. And I will use a time scale f minus 1. Okay, so basically, and I will use a depth scale, maybe, I'm not sure how to say it. Depth scale h0, so I don't know, x, y will be root g prime h0 over f, x tilde, y tilde, time will be f minus 1 t tilde, u, v will be root g prime h0, u tilde, v tilde, psi will be g prime h0 over f, psi tilde, etc. Okay, so you substitute, and h will be h0, h tilde. Okay, you substitute, and so I'm just going to erase stuff on the board because I think you're not supposed to do this, but we're grown-ups, so I'm going to erase f here, h0, and g prime. Okay, so you get these equations where you have no parameters anymore. Okay, so that's the dimensionless version, and I'm immediately dropping the tildes on the dimensionless variables. Okay. And now we're going to introduce an ansatz and carry out an expansion, okay, of the system. Well, not quite immediately. In fact, I first want to introduce the complex velocity, this curly U that I've introduced, which is convenient to isolate maybe the structure of the linear problem. Well, of the non-modulated waves, I should say, because everything has been linearized already around the background flow. So I'll introduce u, now a function of x, y, t, right? So it's u plus iv, which means that, u is u plus u star over 2. U star is complex conjugate. B is u minus u star over 2i. Okay, so if those are equations 1, 2, and 3, we're going to form the evolution equation for curly u through the combination 1 plus I2. Okay, so there's going to be a dt of u. These Coriolis terms will lead to plus IU. This is the linear problem that I've solved before, pure inertial oscillations. There will be a plus j of psi curly u. That's this advection. These terms are a bit of a mess, but you can substitute, and I'm just going to show you what you get. Fairly standard, so you get plus I over 2 u times Laplacian psi. This is the vorticity of the background flow. And then there's a term in u star plus u star over 2 times, what's in here? Minus 2 psi xy minus I psi yy plus I psi xx. Okay. And on the right-hand side is minus dx of h minus I dy of h. Okay. Minus I dy of h. And I also need to write the h equation in terms of this curly u variable. Okay, so I'll have dt of h plus j of psi h. And on the right-hand side, I will have minus the divergence of this. Yeah, so that's minus dx of u plus u star over 2 minus I dy, sorry, divergence, minus dy of u minus u star over 2I. Check. Yeah, that's it. Okay, that's really straightforward. Just have to do it. And now we're going to expand the system. So we're going to consider let's see, slowly modulated weak waves in space and time. Is that it? Yeah. And basically, all the words are important here. So weak waves, we're linearizing the system. So to some extent, we've already done that. Slowly modulated in space. So that's because we're going to assume, like I told Giovanni, that the background flow has a scale much greater than this lambda that we've used to non-dimensionalize the horizontal scales. Okay? And if the background flow has a scale much greater than lambda, then the wave field will inherit that horizontal scale, so it will be at a scale much greater than lambda, and so the wave field will remain in the near-inertial wave regime where dispersion is small and the frequency is close to f. Okay? So if you want the background flow to distort the wave field but keep it in the near-inertial wave regime, you need the scale of the flow to be much greater than lambda. And it will be slowly modulated in time because if the flow is not too fast and you're in that regime, what you're going to get is the previous inertial waves to lowest order, but the complex amplitude of the waves will evolve slowly over a slower time variable, so we're going to be doing that multiple time scale expansion. Okay? So here are the scalings we're going to consider. There will be a small parameter epsilon much less than 1, which you could consider, for instance, as the ratio of lambda over the typical scale of the background flow. Okay. And so we're going to say that psi is some psi 0 of capital X and capital Y, okay, where X and Y are slow spatial variables. Okay, so that's saying that the scale of the flow is much greater than lambda. We're going to expand U. U will be epsilon U1, and U1 is a function of capital X, capital Y, little t, and some slow time variable capital T, plus epsilon cubed U3 of the same variables, plus blah, blah, blah. And H, deformation of the interface, will be epsilon squared H2 of xy t plus higher order terms. Okay, so here capital T will be epsilon squared t. Okay, this is the slow time variable in which we're going to get some non-trivial evolution of the amplitude of the near-inertial waves. You can see I'm doing something a bit weird here. I've scaled U and H with an epsilon here. I don't need to do that once I've linearized the shallow water equation, but had I started from the full shallow water equation, this would be the justification to linearize the equations. Then nonlinear terms would be negligible. Okay, so to some extent, that's to justify linearization, but since I've already linearize the equations for brevity to show you what happens. This, you could say this is unnecessary at this stage.
Just so you're not considering that the waves are slower than the mean flow or fast, have a length scale. They are the same length scale as the mean flow.
That's right. So in fact, So here I'm insisting that the scale of the wave field and the mean flow is greater than these Rossby deformation radius lambda that's in the problem, which is the scale at which dispersive effects would be really strong. Okay, and I'm insisting that this is the case using this change of variables here. But I should say maybe, here it looks like I'm introducing a multiple scale expansion in space, but really I'm not. I'm just rescaling the x and y variables, and you can see there's only x and y in here. Whereas in time, I will be keeping two time variables, so now any time derivative will becomes d fast t plus epsilon squared d small t.
But doesn't that mean that in your original non-initialized system, you picked the wrong length scale?
That's one way to see it. I've non-dimensionalized the system using the typical scale at which the flow would become, the waves would become dispersive. So then I'm saying, I need a slower scale, a slower spatial scale than that if I want things to remain non-dispersive. I could have non-dimensionalized stuff using directly the scale of the mean flow. And then, then spatial derivatives would have been of order 1. But I think then you don't quite see what these scales should be large as compared to. It's a matter of taste. I seem to have different taste than most people for this. So maybe you're right. But still, at this level, now we can do whatever we want.
Are these exponents intuitive? It's a more favor than I have. Could I guess that this epsilon square as well as
Well, yes, I guess. You always can. The question is, do you guess the exponents before or after you try the expansion? But one way, can you? Yeah. So I don't know how people did it. Typically you try, you don't get the terms you want in the solvability condition. Think, if these were bigger, it would arise in the solvability condition. So I think the truth is this is how people probably did it, Young and Benjelloul initially. But now, yes, you can guess some things. For instance, I showed you that the dispersion relation was, omega squared equals f squared plus a small correction in k squared. Okay, so the frequency will have a correction in k squared. Okay, and k is very small. It's of order epsilon because the scale is so large as compared. So if I want to get dispersion in the equation, I want the term of order epsilon squared due to this k squared to arise in my solvability condition. And this k squared, this dispersion, it's of order epsilon squared, so it should arise on this time scale here of order epsilon squared. Okay, that's one of them. You can see that any advection here is two spatial derivatives. So these epsilon squared will have to be comparable to the slow time evolution as well of the system. So, but basically, it's counting epsilon, and then you can make up the nice arguments that you would use beforehand. But yeah, so probably, yeah. Okay, let's do it, I guess. So this would be equation 3, and that would be 4. So we're going to start with equation 3 at order epsilon. This will be dt of u1 plus I u1 equals 0. Right? Any spatial derivative adds a new epsilon in the problem. So this would be of order at least epsilon cubed. Right? Two derivatives here. That's way too high order. And on the right-hand side, it's epsilon cubed to begin with, spatial derivative and epsilon squared. Okay, so u1 is m e to the minus it. This is the non-dimensionalized version of the inertial oscillation. But now m is a function of capital X, capital Y, and capital T. Okay? And as usual, we're going to go to next order to get an evolution equation for this complex amplitude of the near-inertial wave field through a solvability condition. Okay, so we're going to write 3 at order epsilon cubed will be the next order term. So let me see. dt of u3 plus iu3. Then there will be a dt, d capital T of u1. This is the first two terms. There is a j of psi 0 u1. Two derivatives is epsilon squared. So it's a j with respect to the slope variables, x now. There is a plus I over 2 Laplacian psi 0 u1. Okay, and again, this Laplacian is with respect to the slope variables now. And then there is u1 star over 2 times the bracket. Okay, and on the right-hand side, I have minus dx, d capital X of h2 minus I d capital Y of h2. Okay? So I'm going to write this, as usual, by isolating the linear operator on the left-hand side, dtu3 plus iu3, dtu1 minus j psi u1 minus I over 2 Laplacian psi u1 minus u1 star times this bracket minus dx of h2 minus I dy of h2. Okay? And then I'm going to say, well, on the left-hand side is this same linear operator, which is these two oscillations going like e to the minus it. So there will be a solvability condition that on the right-hand side, I should have nothing that behaves as e to the minus it, because otherwise that would drive secular terms in u3 and the expansion would break down. Okay, so solvability condition is no e to the minus it on the right-hand side. Okay, so we're going to see what all these contributions give in terms of e to the minus it. So for instance, minus dt of u1 will lead to, so this means amplitude in front of e to the minus it. Well, where's u1? u1 is thank you. Okay. So this will be minus dt of m, e to the minus it. This is the resonant part of this term. There is minus j of psi m. This one will lead to minus j of psi u1 leads to minus j of psi m. Those ones are easy. Minus I over 2 Laplacian psi u1 leads to minus I over 2 Laplacian psi capital M. U star times the bracket. U star is e to the plus it, that's non-resonant. This leads to 0. And the last term I have to deal with is the h2 part. Okay. So to compute the h2 part, I need the resonant part of h2. That's the part of h2 that behaves as e to the minus it. Okay, and so the resonant part of h2 is obtained from equation 4 at order epsilon squared, which is dt of h2. This is 2 high order, so I only have the stuff on the right-hand side. I'm going to write res to mean I only focus on the resonant part. U star is non-resonant, so I only keep the U term. Okay, so I have minus 1/2 d capital X of U. Okay, so that would be, And then I have minus 1 over 2I dy of capital U. Okay, this is a fast time derivative. All of that is e to the minus it. So this will be minus I H2 resonant. Okay, so I get H2 resonant from that. And I substitute in here. Okay, and I obtain, okay, so here are the steps. It's fairly straightforward. And this minus dx of H2 minus I dy of H2 will give you the resonant contribution. Which one is it? It's I over 2 Laplacian of m. Okay? So it's this k-squared contribution that comes from dispersion, in fact, that you get here. Okay, so the solvability condition then becomes dt of m plus j of psi m plus I over 2 Laplacian psi m minus I over 2 Laplacian m equals 0. And this is the simplest instance of the Young-Benjelloul equation. Okay, then there's the YBJ equation. This particular derivation, I think, is due to Danu, Vanes, and Buehler 2015 in a JFM paper. I don't know, maybe it comes from somewhere else, but it's very well explained in this paper. And Young and Benjelloul did that in 97. Okay, and so you can see various terms in this equation. So this is, of course, the complex amplitude of the wave field that's evolving as a function of time. You can see there is advection by the background flow. Okay, so this is the advective term. This one is known as the refractive term. So there's a refraction, and we're used to the vorticity of the background flow deflecting wave packets in the ray tracing limit. So maybe that's why this one was called the refraction term. And this one is dispersion. Okay, you can see the mean flow is not involved in this term. So if I had no flow, I would just have this term, which is the first correction in k squared to the inertial frequency. Okay? So typically, and in the following, I will be studying the solutions to this problem, to the YBJ equation. I don't know, maybe that's 5. In a domain D, that's doubly periodic. So I guess I should call that the torus now. 0. So that's x and y in 0 L squared. I mean, quickly I will revert to small x and small time and stuff once we know how to derive the equations. I just use all lowercase letters. With the initial condition that m of x at time equals 0 is just equal to 1. Right, the equation is linear, so I don't care about the magnitude. I'm going to set it to 1. The equation is invariant to a phase shift of m, so I'll just pick it real. Okay? So maybe one question, has anyone already seen that equation in a different context? As I erase the board. No? Yeah, you're close, you're close. Okay, if I multiply it with I, able to? No, maybe? Yeah, it looks like a Schrödinger equation, right? And in fact, in the same paper by Daniel van Esbuller, they say if you get rid of this term, it's really a Schrödinger equation, right? You would have the Laplacian term, and you would have Laplacian psi that plays the role of a potential, right? And in fact, I'm going to claim that it's exactly the Schrödinger equation for a slightly more complex system, okay, but not very complicated. And there's a, I don't know, call it a quantum analogy. And I should say maybe I'm about to make an analogy with a problem that's even more complicated than the initial problem, but I claim that eventually, in the next lecture, this will prove useful, okay? So maybe you remember how you would describe a charged particle in a steady, static electromagnetic field in quantum mechanics. So you would write a Hamiltonian that's hammer 2. Then we have P minus QA, the vector potential squared. And then you're going to have Q, V of x, the electrostatic potential. And P in quantum mechanics is minus h bar times gradient. Okay, reminds you of something. And then the Schrödinger equation will be a h bar dt of phi. The wave function is h applied to phi. Okay. This seems to be the right Hamiltonian. So now I'm going to choose units such that m equals h bar equals q equals 1. That's really just my way of non-dimensionalizing this problem. And the following potentials. So let's see. A will be simply the curl of the stream function of the background YBJ flow. So it's minus the velocity because I had the minus sign in the GFD convention. And V of x will be 1/2 of Laplacian psi minus grad psi squared. Yeah. So I'm going to substitute in here. Yeah. So I dt of phi will be, I have 1/2 minus I gradient plus u squared plus 1/2 Laplacian psi minus u squared phi equals 0. So this thing here is minus Laplacian. U is divergence free. Oh, that's convenient. So I get minus 2i u dot gradient plus u squared. So this whole thing will be minus 1/2 of the Laplacian minus I u dot grad is j of psi phi. U squared cancels with this, and I have plus 1/2 Laplacian psi. So if I'm not wrong, this should be exactly this equation up here. And I think it is, yeah. Okay, so this is the YBJ equation written for phi, for the wave function of this particle. Okay? So we can write a few analogous quantities between the two systems. Let's see, so we have the quantum particle. And we have the YBJ system. So we said that there's a wave function phi. The equivalent will be the complex amplitude m. There's a vector potential. Which was the curl of psi z. So the equivalent here is minus the velocity field. Okay. There is a magnetic field. The magnetic field is the curl of the vector potential. So it will be minus Laplacian psi along z. Okay, so here again, this will be minus Laplacian psi along z. And already you can get some intuition. If it's a charged particle with unit charge that's propagating in a magnetic field, you expect this magnetic field to deflect the wave packet. So when I told you that in wave mean flow interaction, it's pretty usual that the vorticity deflects the wave packets in the ray tracing limits. Well, in the ray tracing limit, I mean classical mechanics, the wave packets are particles, and indeed they're going to be deflected by the Lorentz force here. Okay, so vorticity deflects the wave packets. What else? Well, there's an electric potential. V, and its equivalent is a minus 1/2 of yeah. Okay, so yes.
In the electromagnetic quantum situation, can you freely choose A and B, or are they linked by some electromagnetic equation?
No, you can freely choose them.
Okay.
Yeah, and in fact, you may have several choices. You have a choice of gauge. In this context, it's pretty, a convenient choice of gauge is to demand that the vector potential be divergence-free, because then it has this direct, yeah. So in fact, this analogy is present, in various forms in the literature. So, in your paper, you just discarded this term and discussed the Schrödinger equation with a standard potential. In an earlier paper by Baumforth, Rolling-Smith, and Young, they identify the fact that this advective term is a magnetic term, should be magnetic field, but then, they disregard the potential and say it looks unphysical for some reason. I claim that we can keep both and get this analogy. And again, at this stage, it might look a bit, why am I doing this? I claim that the analogy is useful to make quantitative predictions, but we'll see that in the next lecture. Okay. So some things we can do, as any analogy, once you've seen it, you don't need it anymore, because you can transpose all the techniques from the other problem into your problem of interest, and you don't need to mention the analogy anymore. But there are some nice things you can still do. For instance, if we're interested in the conserved quantities of the YBJ equation, okay. Well, so there's two quantities, in fact, that are immediate from the quantum analogy, which is that we're going to conserve the probability, right, of the total probability. So that would be the integral of phi squared dx over the domain D. Okay, and so here, this leads to conservation of the integral of m squared dx. And in fact, I'm going just to introduce a space average. Okay, so that's a space average, which I will be using extensively over the domain D. So of course, you don't quite need a quantum analogy to see that. You can just get this equation, multiply by m star at the complex conjugate, integrate over the domain. Okay. And this is the kinetic energy of the near-inertial wave fields, right? U squared plus b squared. Maybe there's a 1/2, but I'm going to disregard it. And also in this context, in fact, this is also the action of the near-inertial waves, because for near-inertial waves, the kinetic energy is larger than the other forms of energy, like potential energy and stuff. So the dominant form of energy is kinetic energy. To get the action, you would divide that by the frequency, but the dominant frequency is f. You know, everything is close to f in terms of frequency. So in fact, this is also the action of the wave field in this context. Okay, so this one is maybe trivial, but useful. There is another one, quantum mechanics. The Hamiltonian is independent of time. So we're going to conserve the energy of the particle. And the particle's energy is psi h psi. So in the present context, it will be the average of m star times h of m, where h of m is just the right-hand side of, I've just erased it. It was the YBJ equation that I multiplied with I. Okay, so it was I dt of m equals minus I j of psi m plus 1/2 Laplacian psi m minus 1/2 Laplacian m. So that's the h of m. So if I substitute this, this will be the spatial average of, I'm going to integrate this one by part. I will get grad m squared over 2. This one will be 1/2 Laplacian psi m squared. And this one will be minus I m. I'm going to integrate by parts. Write this like this, maybe. Okay? And so that's the second invariant. In fact, it took some time for people to identify this invariant. It was identified again in Danu, Van Est, and Buehler, 2015. Almost 2 decades after the YBJ equation was uncovered. Again, I claim that from the quantum analogy, it's pretty, they got it directly from the equation. Maybe it's straightforward from the equation. Once you realize there's this quantum analogy, then it's, you immediately write the particle energy and you get this invariant here. Several contributions to this energy. This thing here, the gradient of m squared, that's the dominant contribution from the potential energy of the waves. This one is just, the refractive part. I'm going to call that refraction. And this one is due to advection. Okay, we covered the 3 terms of the equation. Okay, and so I told you that maybe the near-inertial waves would accumulate in anticyclones. So here's a hand-waving argument due to Danu, Van Est, and Buehler again. So in the initial condition, should give a name to this. Maybe capital E. Okay, so here we have conservation of probability, which translates into conservation of this, and we have conservation of energy, which leads to conservation of this E here. And so the initial condition is uniform. So if M is uniform, then this is 0, this is 0, and this is 0 because the vorticity has a vanishing average in the 2D domain. Okay, so E equals 0, and E is a conserved quantity, so E is 0 at any time. So Danu, Vaness, and Buehler say, among other things, if we neglect advection, then as time evolves, the field will gain some structure, and surely this term will go from 0 to positive. And if you neglect advection, then the conclusion is that this term here should be negative. Okay? And what does it mean? It means that this energy, kinetic energy of the near-inertial wave field, it should be correlated with regions where Laplacian psi are negative. Again, that's anticyclones. Okay, so near-inertial waves accumulate in anticyclones. Okay, of course, it's not very quantitative at this stage. You have to neglect this term. It's not obvious when you can neglect this term or not, but that's the idea. Okay, so let me see. What else do I want to say? Yeah, so the goal here is to revisit these statements and try to make some maybe more quantitative statements, and I'll be focusing on two limits for that. The limit where the background flow is very weak, and the limit where the background flow is very fast. And the limit, to some extent, the limit of weak background flow has been in the literature since Young and Benjelloul, although we pushed it to higher order. But the limit of the fast background flow was absent as far as I know. So basically, to revisit and predict statistics, we're going to consider two regimes of interest. Depending on the strength of the background flow. And to make this strength clear, I will rewrite the stream function psi of xy as some strength gamma of the stream function times chi of xy, where chi has unit variance. Okay, the average of the domain. Then the equation 5 will become 1 over gamma dt of m plus j of chi m plus I over 2 Laplacian chi m minus I over 2 gamma Laplacian m equals 0. Okay, and the two limits will be gamma much less than 1. That's when the dispersion here is really strong. So that's known as the strong dispersion regime. And in terms of the analogy, that's also the strongly quantum regime, where you have these, Laplacian of the free particle maybe, and these terms are much smaller here by a factor of gamma. Okay, so the potentials are much smaller. Okay, So here, we're going to make predictions based on a standard assumption, maybe like you would do in any problem, including quantum mechanics, by expanding for weak potential. And the other limit, which is maybe for more challenging, is the strong advection limit. And if you look at this strong advection regime, where typically it's complicated, right? You have advection of M by this background flow. Large gamma is some kind of large specular number. Although you don't have a diffusive term, you have a dispersive term here, so you have an I. But you have this advection operator by this background flow, which could be anything. It's prescribed, but it could be anything. So a priori, it's a more difficult regime. On the other hand, based on the analogy, you can see that's when these two terms are very small. So this is the H bar going to 0. And in fact, it's the limit of classical mechanics for the analogous system. And that's good news because we have tons of techniques to deal with classical mechanics problems. So in fact, we'll be able to say some things in that regime as well. Okay, in particular, based on Newton's third law, you would say that, the field would look like wave packets, and the trajectory of a wave packet would follow the equations of classical mechanics. So mx double dot equals q e, which is minus grad v plus x dot times b, the magnetic field. Well, the magnetic field was, what was it, Laplacian, minus Laplacian. Okay, so you can immediately write the ray tracing equations, for instance, from your knowledge of classical mechanics. You don't have to carry out the expansion. That's something you gain for that. Okay, but this I will discuss very much during the next lecture. In fact, I'm running late. One last thing I'd like to do is to quickly discuss this first gamma smaller than 1 regime. Okay, and show you how you can make predictions using an expansion. And I'll just show you the first correction. So for gamma much less than 1, we're going to expand M. M will be 1. The initial condition is kind of driving that. And then there will be a correction, gamma M, and then order gamma squared. And we're going to impose that the spatial average of M is 0. I guess that's probably sufficient. I'm going to write, is that 6? Let's see, I have the gamma downstairs. So this is maybe order 1. I will have dt of m here. That's order 1. I have j of chi m would be order epsilon. I have I over 2 Laplacian chi times 1. Yeah. And then I have minus I over 2 Laplacian of little m equals 0. Okay, so maybe dtm minus I over 2 Laplacian m equals minus I over 2 Laplacian chi. And so the solution to this will be m equals, well, there's an easy particular solution. It's m equals chi. And then there will be an m tilde, okay, solution to the homogeneous equation, which is here just to enforce that little m is 0 at t equals 0. Okay. It's really easy to compute m in terms of the Fourier coefficients of chi, for instance. And one consequence of this is that m tilde time average is 0. So this here is a time average. Okay, so we can compute this m tilde. I'm not going to do it because it's not particularly enlightening. You know, it's expressed in terms of the Fourier coefficients of chi. I'll just show you what predictions we make using this simple lowest order strong dispersion expansion. For instance, the near-inertial wave kinetic energy. So m, we said, is approximately 1 plus gamma chi, that's psi, xy, plus gamma m tilde. Okay, but here these two terms are of the same order. Okay, m squared, the kinetic energy, then is approximately, if I time average it, I get 1 plus 2 psi of xy, and the m tilde contributions vanish on time average. Okay, so you get that near-inertial wave kinetic energy will be modulated, but modulated by the stream function of the background flow, not exactly by the vorticity. So, you know, this psi could look like the vorticity field if, for instance, the background flow has a single wave number, but, you know, generically it could be different. Grad m squared would be 1 plus, is it 2u squared? No, there's no 1. Once again, that's u squared plus grad m tilde squared, average over time. Okay, and we've computed this, and you can test this prediction again. Maybe one last thing, which I'll just mention, but yeah, I won't have time to go into the details. You can also compute the Stokes drift. That's really for those of you who are experts in wave dynamics. So the Stokes drift would be psi dot grad u, where psi, so that's us. I'm going to average it over time, where psi is the wavy displacement, defined by dt of psi equals u, the fast oscillation at the inertial frequency. Okay, so you can substitute in here. If you substitute our expression for u, for near-inertial wave fields, you can show, as an exercise maybe if you're interested, that us is a quarter of I m grad m star minus m star grad m. You may recognize the current of probability in quantum mechanics. And then you also have another term, curl of m squared easy. Okay, that's just substitution of our lowest order expression. And so here, for gamma much less than 1, in our expansion, in fact, this term will turn out to be negligible. We'll get this one. We said that m squared was modulated with a 2 psi term. So we'll have twice the curl of psi with this one. So that's minus 1/2 times the background flow, capital U of xy. That's what we'll get. Okay. So I'll just finish by showing you some numerical results on this system. So this is from Daniel et al. 2015. So I think I've mentioned many of the arguments they have. This is their vorticity field here. And you can see that for intermediate flows, which is this middle picture here, you can convince yourself that there is indeed some correlation between anticyclones, which would be blue regions in this figure, and dark red regions in this middle plot. Of course, they also have some quantitative metrics, but you can kind of see it. When the flow is very slow, that would be gamma much less than 1, or very fast, gamma much greater than 1, it's not entirely clear that you have this correlation. And I mentioned it, and there's been subsequent papers. What happens here? Why don't we see such a strong correlation in anticyclones? Okay, so we've revisited this. Okay, I've mentioned these questions. We want to make predictions, and we've made predictions in the low gamma regime. I'm going to show numerical simulations that were performed by Alexandre Klili. And in fact, a lot of our recent work on the YBJ equations is work done with Alexandre Clélie, especially what I'll be showing in the next lecture. So this is our background flow. The background flow is just a snapshot from a solution to the 2D Navier-Stokes equation that was provided to us kindly by Julie Meunier. And so we take this snapshot and we use it as a steady background flow, time independent, okay? Even though it came from a time dependent simulation. So it's a time independent flow. You can see the stream functions, 2 anticyclones, 1 cyclone here maybe. In terms of the kinetic energy, you can see some smaller scales in the system. It's kind of multi-scale. And this is the vorticity here. Okay, so we use that as background flow for all the simulations. In the strong dispersion regime, I'll be using a small gamma. It's 0.05, so really small. You can check that indeed these, as you expect, this expansion works. So that's the numerical results. That's the prediction that I've shown here. We also went to next order to extend that to higher order, to higher values of gamma. This is the wave potential energy, again from Alexandre's numerics, and based on the prediction where we've included this grad M tilde that was disregarded by Young and Benjelloul, but mentioned by Danu, Van Esten, and Buehler. So we've computed it and checked that indeed it contributes to this potential energy if you want to get good agreement. And that's the Stokes drift, which indeed, as expected, is just directly opposite to the background flow, which is, so it's quantitative both in terms of structure and magnitude. So we're quite happy about that. Again, this is kind of a straightforward expansion, so we expect things to work, but it's still nice to check that. Okay, I'm going to stop here for the first lecture. So I hope you've understood what near-inertial waves are, why we care about them for the ocean, how the equation is really nice, linear, and looks like a Schrödinger equation. To some extent, I've shown you the easy limit here of predicting the statistics of the wave field. And tomorrow, I will be discussing maybe the more challenging strong advection limit of this near-inertial wave problem before turning to internal gravity waves and doing things different. All right, thank you.